Hi everyone, this is our overview of the organic chemistry unit. The unit started by us thinking about what does organic even mean in a chemistry context. It's chemicals that contain carbon. However, there are four groups of exceptions where a chemical could have carbon but is not classified as organic. These are carbon oxides, carbon monoxide and dioxide, carbonates, CO3 2-, cyanides, CN1-, and carbides, C2-. A nice rule of thumb is to say that organic compounds are always molecular. So if there's a metal, if there's any ions happening, that's going to disqualify it from being organic. From there, we introduce some new number prefixes. 1 could be meth, 2 eth, 3 prop, 4 bute, and 5 through 10 were what we were used to. From there, we worked our way through, it turns out to be 11 groups of chemicals, their naming rules, whether they're saturated or not, even a general formula. Starting with alkanes. These are straight chain hydrocarbons where it's always a single bond in between all of the carbons. They have a general formula CnH2n plus 2, and they are classified as saturated compounds. Alkenes have a double bond. They're CnH2n. They're unsaturated. Very similar are alkynes. These are linear hydrocarbons that have a triple bond somewhere in their chain. They have a general formula CnH2n minus 2, and they, like alkenes, are unsaturated. We took those three groups of chemicals, and then instead of having linear chains of carbons, we saw they might make a ring structure, a cyclical structure, and so we have cycloalkanes, cycloalkenes, cycloalkynes. They have a geometric shape to represent the ring structure of 3 or 4 or 5 or 6 or 8 carbons. If they're all single bonds, then we have a cycloalkane. They have the same general formula, CnH2n, as alkenes. Cycloalkenes have a double bond in that ring structure. They're CnH2n minus 2, just like alkynes. And cycloalkynes, they have a triple bond and a general formula, CnH2n minus 4. From there, we introduced another type of ring structure, a benzene ring, a hexagon with a circle in it, with 3 double bonds. This is classified as aromatic. All other types of compounds that do not have a benzene ring are classified as aliphatic. But if we see that benzene ring, whether it's a branch called phenyl or a benzene ring itself as the dominant structure, those are aromatic. So an important way of classifying chemicals is, are they aromatic or aliphatic? But a second way is it saturated or unsaturated? After aromatics, we started to work our way through hydrocarbon derivatives. We saw halides. Maybe there's a fluorine, chlorine, bromine, or iodine somewhere in the chemical. Maybe we have this OH, a hydroxyl, to tell us we have an alcohol. A carboxyl, a double bonded oxygen and an OH at the end of a chain, carboxyl. We're able to identify a formula that has a COOH at the end of the formula for our carboxylic acids, and we ended with esters. That's 2 different carbon chains separated by an oxygen in the middle, and immediately to the left or the right is a double bonded oxygen. There's an alcohol side and an acid side to an ester, and it really has some important consequences for our naming rules. After working our way through the naming and drawing structures for 11 classes of compounds, we started to work on reactions. Our first reaction was one that was really familiar to us, hydrocarbon combustion. We've been working on it since grade 10. We know what to do about hydrocarbon combustion. Let's just be careful. Let's be careful counting up carbons and hydrogens. Let's be careful with our balancing. From there, we had an addition style of reaction. It's where we have an unsaturated alkene or alkyne undergoing a reaction with maybe excess or limited amounts of another reactant Here with addition, we really have to be careful with the presence of isomers. After addition, we worked substitution. Here we have a saturated hydrocarbon reacting with a halogen or an alcohol or something like that, and a switching is happening, an exchange. So we end up with an inorganic product when we do substitution. An important way that we're able to tell addition or substitution apart is by doing this thing called the bromine test. Bromine has this orange rusty color. If the color persists, if the orange stays around after the reaction, that's a sign that we had a substitution reaction and the original chemical was saturated. However, if the orange color disappears and it turns colorless, then we knew that we had an addition reaction and the organic reactant was unsaturated, was an alkene or an alkyne. From there, we worked on one very specific form of elimination where we have an alcohol reacting in the presence of a catalyst. We're going to remove water, HOH. It's really important that we're going to form a double bond. We're going to take a hydrogen from the carbon with the most carbon-to-carbon bonds. Esterification really connected with our work on esters itself. A carboxylic acid and an alcohol react together, take water out, dehydrate it, undergo condensation to form that ester. Esterification is one of the few places where we might have to work backwards from the products back to the reactants. After that, we had a moment of work on polymers and polymerization, an individual chemical, a monomer, but many monomers linked together, a polymer. They occur in nature, they occur in organic chemistry. They're polyesters, they're polyamides, they're even chemicals that might look like an alkane. We're going to be able to classify polymerization as addition polymerization or condensation polymerization. That's a thing to watch out for. After all of that, the last topic of the unit was about refining hydrocarbons. Remember, we do fractional distillation. We take advantage of the physical property boiling point. Shorter chains have low boiling points. Longer chains have higher boiling points. We're able to isolate the different components of crude oil by doing what's called fractional distillation. It's a tower, multiple stories tall, that's extra hot at the bottom, cooler at the top. And we're able to collect or harvest larger chemicals from the bottom of the tower. And as we move up the tower, we're going to find smaller and smaller hydrocarbons. The final thing is about solubility. Alkenes and alkynes, they're not soluble in water. Oil and water don't mix, they're not soluble. Whereas our hydrocarbon derivatives, alcohols, carboxylic acids, and esters, they are soluble in water. However, as the chain gets longer and longer, these molecules become less and less polar and become less and less soluble in water. It's a whirlwind, our work on organic chemistry. We covered a lot of ground, from just introducing new number prefixes all the way through our 11 classes of compounds, a bunch of new reactions, and even a brief overview of how oil refineries work. I would invite you to look back at other videos in this unit, and good luck on your exam. I hope that helps.